Hi, in this video I'm going to prove the statement we had in the previous one on continuity of measures. The theorem we want to prove here is the one on continuity of measures. So it says that there are four conditions which are equivalent for a finitely additive measure on an algebra. The first one is that the measure is actually the finitely additive measure is actually a measure. The second one is that for increasing sets, the limit is the limit of the probabilities or limit of the measures is the same as the probability of the union. The third is that for decreasing sets, the limit of the measures is the measure of the intersection. And the fourth is that if the sets are decreasing to zero, so the empty set actually, then the limit of the measures is again the measure of the limit, which is the measure of the intersection, which is empty, and measure of the empty set is always zero. Okay, so let's prove them. I'm going to do this in 4 steps. So I'm going to prove 1 implies 2, step 2, 2 implies 3, step 3, 3 implies 4, and step 4, 4 implies 1. And that will give you a full equivalence then. Okay, so proof of 1 implies 2. So 1 implies 2. How can that happen? So let's assume what we want to talk about is an increasing system of events. Okay, so take some increasing events here. So A1, A2, A3, maybe let's put A2 in here, and A3, and then and so on and so on. So we have larger and larger sets. Okay. And what I want to introduce is the increments, the disjoint increments of these sets. So I'm going to start with B1 equals A1, and for I at least 2, I'm going to have BI equals AI minus AI minus 1. So A1 is B1, then B2 is going to be A2 minus A1, so B2 is all of the increment from A1 to A2, and then B3 is going to be A3 over minus A2, so B3 is all the increment from A2 to A3, and so on and so on. So it's all these sets increment, the new pieces which are added in the consecutive A's. And now I can start a chain of equalities. So if I look at the union of all of these events, then I can break this up into the union of the increments. So why is that true? Well, if we are in any of the ANs, that's exactly when we are in this union, then we are of course in some of the BNs, because at some point we have to be included as an increment in these sets. And that includes B1 possibly. So if we happen to be in A1, then of course already we are in B1. So either in B1 or in one of these increments we are in. But the point is that the B's are disjoint. So the BI's are exclusive, disjoint. And therefore, assuming 1, which said that P is a measure, so if I have any countable number of these B's, then the probability of the union, because they are exclusive, so this and also assuming 1, implies that the probability of this union is going to be the measure of this union is going to be the sum of the measures. Okay? And that's an infinite sum in general, which is of course the limit of the finite sum. So I can take a finite sum up to k of the Bn probabilities or Bn measures. Okay, and so now I can plug back in what the probability of Bn is. So if I do a let me copy the limit, k goes to infinity. Let me do this sum from 2 to k for the first term, and there when Bn is at least 2, then AI minus 1 is what BI is, or AN minus 1 is what BN is. And notice that AN, or so well, notice that AI, let me use I, is entirely containing AI minus 1, because it's an increasing system of events. And therefore, if I look at the set difference, of these events, then the probability of that is going to be the difference of the probabilities between an and an minus 1. So again, if one draws a picture, then this becomes quite clear. So here is an minus 1. The increment to it is bn, and that results in an. And so the union of an minus 1 and and bn is an, and these two are also disjoint or exclusive. And this means that the probability of an minus 1 plus the probability of bn is the probability, or measure if you want, of an, and that's what we use here. So rearranging this exactly gives that. Okay? And then at the end, I still have to write the n equals to 1 term, which is a p of b1, but b1 is a1. b1 is a1, so p of b1 is just p of a1 at the end here. And so now, if you start expanding what this difference means under the sum, it becomes a telescopic sum. This is a telescopic sum, and the first term is going to be a minus PA1. That's the one thing that survives on the lower end. So let's put a lim k goes to infinity. So on the lower end, a minus p a of n equals to 2 minus 1, so a1 survives. On the upper end, a p of a k survives. And then there is also this last addition plus p of a1. And we're done, because what we proved is that we have, let me end it here, what we proved is that we have the limit as k goes to infinity of p of ak, and that's exactly what we wanted to show. The probability of the union is equal to the limit of the probabilities. Okay, so now 2 is done. So 1 implies 2 is done. Okay, the next step is 2 implies 3. So let's do the proof of 2 implies 3. Proof of 2 implies 3. So what do we want to prove? 2 was that for increasing events, the limit of the probability is the probability of the union. 3 is that for decreasing events, the limit of the probability is the probability of the intersections, assuming that unions and intersections are still in my algebra. Okay, so how do we do that? So we want to say something about 3, so we're going to take a decreasing system. Let a and b decreasing in n. What does that mean? That means that here is a1, and then a2, and then it goes down to an, and somewhere in an we have the intersection, and it could be the intersection could be empty or could be something non-empty. Okay, it shrinks down, further down and down. And let's start writing the limit as n goes to infinity, probability of an. Now here is a little trick we can do. We could say that if I look at a1, that's going to be again the union of an and everything missing, so a1 minus an, where this is a set theoretic difference. So an is this little piece in here, and then a1 minus an is all the increment from an to a1. These two are disjoint, and together they give back the event a1. And that means that the probability of an, again, this is the same trick as before, can be written as the difference between the probability of a1 and the probability of that increment. So I'm going to write p of an as the probability of all of these things, which is a1, minus the probability of going from a1 to an, or an to a1. Okay, so again, the reason is that if I look at probability of a1, it's going to be the sum of the probability of an and probability of a1 minus an because of this disjoint union here. All right, and the point is that a1 minus an is an increasing system. If I go further in n, then I'm going to have something inside here. The difference from a1 to that is larger than the difference from a1 to an. As I shrink an down, the difference is increasing in size. So more and more points are included in the difference a1 minus an as n increases. And that's the point, because at this moment I can use number 2, which said that for increasing events, the limit of the probability is the probability of the union. So if I pass the limit through the a1, which I can do because there is no n in here, I pass the limit in here, then the limit hits this probability, and because it's an increasing system of events inside, the limit makes a probability of the union out of those increasing events, a1 minus an. So this is because of the assumption 2. Okay? And now everybody can convince themselves that the union of all of these differences is equal to the union of all of these differences is equal to the difference between a1 and the intersection of the an's. This is something like De Morgan's law. You can convince yourself that exactly those points in this union are included in this difference. Okay? So it's the probability of a1 minus the intersection of an. But then again, if you carefully look at the intersection of an's, and the union of a1 minus this intersection of the an, these are two disjoint sets, and together they give me a1. So these are disjoint. Oops. These are disjoint. And their union is a1. And therefore the probability of a1 is the sum of these two probabilities. So if I do probability of a1 minus probability of this part, then I end up with just the probability of the intersection of an. And at this moment I'm done, because I have this decreasing system an, and I just proved that the limit of the probabilities is the probability of the intersection. So that's exactly what I wanted to do. Limit of the probability is probability of the intersection. So now this is done. So 2 implies 3 is done. Okay. 3 implies 4 is trivial, because 3 says that for any decreasing system, the limit of the probability is the probability of the intersection, and 4 says that for a particular type of decreasing systems, namely with intersection being empty, the limit is of the probability is the probability of the intersection, which is the probability of the empty set, which is 0. So 4 is clearly just a subspace, subcase of 3, and therefore 3 implies 4 is trivial. Okay, I'm going to record this here. So proof of 3 implies 4 is just trivial. 4 is a subcase of 3. So we're done with that. And finally, I need to show that 4 implies 1. So I need to show that if you have a decreasing system with limit being empty, then the limit of the probability is empty. Suppose that. That implies that P is a measure. Okay, so assuming 4 implies that the probability or this additive measure is also finite additive measure is also a sigma additive, so it's a measure. Okay, so let's prove 4 implies 1. Okay, to this order, let BI be any disjoint sets in the sigma algebra, of course. Everything is, or in the algebra. Everything is in the algebra. Let's assume that the union is also in the algebra. And let's start writing out the sum of the measures or probabilities of these BIs. Okay, so what is the sum? Well, this is the limit as n goes to infinity of the finite sum, just by the definition of an infinite sum. And we assuming all around that we're talking about a finitely additive measure. So as soon as I have a finite sum, then everything is fine. And the sum of the probabilities of disjoint sets is going to be the probability of the union, of this finite union of the disjoint sets. Okay, this is for every n, it's every finite n, it's fine, so I can take a limit in there. Now I'm going to do a little trick here. I'm going to take this limit as n goes to infinity, and I'm going to say that I'm looking at the infinite union from 1 to infinity, and this is fine because I assume it's in the algebra, so I can take a probability of that. And I subtract from that the union, the part of the union which I don't need, namely from n plus 1 to infinity. Okay, so the reason is that this infinite union contains my finite union and the rest. These two are disjoint. Okay, the finite union has b's from 1 through n, the rest has b's from n plus 1 to infinity. The b's are disjoint, so these two unions are disjoint. And therefore I can take the probability of the difference, which is this finite union, is the difference of the probabilities, which is here. Okay, so that's my next step. And now what I want to claim is that this set here as a set, this union from n plus 1 to infinity as a set, will go to, is decreasing of course, decreasing in n, because I'm taking the union of less and less things. So if I take the union of less and less of these BIs, then I can only decrease in size. I'm just taking less and less points in my union. But the claim is that also this will decrease to 0. So as n goes to infinity, the limit is empty. Okay, so why is that? Why is that? Now, there are two kinds of points in my sample space. There are those points which are not part of any of the BIs, possibly. So all I know about BIs is that they are disjoint. So there are some points, if this is my sample space omega, and I have some disjoint sets, okay, so maybe this is B1, this is B2, and so on and so on. There are some points which are outside of the B's, possibly, and they are of course not members of this union. There are some other points which are in some of the B's, but the B's are disjoint, so any point that's in one of the B's can only be in one of them and not more than one of them. As soon as the index n goes past the index of B, if this point is, for example, in B200, if this point is in B200, as soon as n reaches 200, so I start my union from 201, my point is not going to be in this union, because no other B's can contain my point. They are disjoint. If it's in B200, then no other B's can contain my point. So this point will not be in the limit as n goes to infinity, and actually no point will be in that limit as n goes to infinity. Take any point in my sample space, eventually this union goes out from that point. So therefore this decreasing system goes to the empty set. No point can be in this system for large enough n, so in the limit as n goes to infinity. So I can actually apply my assumption, which is statement 4, on this on this union, which I'm going to call AI. So all of, AN, or AN plus 1 maybe. This is going to be my AN plus 1. It's a decreasing system. It goes down to the empty set. So I can apply number 4, which says that the limiting probability is 0. And so when I apply my limit, as n goes to infinity, there is no n in the first part. So it's going to be the union of the BI's. And when I apply the limit on this, I just get the number 0 here. And at this moment I'm done, because what I really needed to prove is that I do have a proper measure here, and I already assumed it's a finitely additive measure. I needed to show that it's sigma additive, so I needed to show that if I take countably many disjoint sets, then the sum of the probabilities is the probability of the union, and that's exactly what happened here. So now the proof is complete.